In question 1, we are asked to use the binomial series to find the expansion of 1 over 2 plus 5x raised to the power of 3 in ascending powers of x up to and including the term in x cubed, and we need to give each coefficient as a fraction in its simplest form. So let's start with 1 over 2 plus 5x to the power of 3. The first thing to do is write this as 2 plus 5x to the power of negative 3. I will now factor out the 2, which will inherit the power of negative 3. And within the bracket we divide by 2, so we've got 1 plus 5x over 2 to the power of negative 3. I'm always trying to attain a form of 1 plus or minus something in terms of x, and then I can proceed. 2 to the power of 3 is 1 over 8, and I will proceed with the binomial expansion of 1 plus 5x over 2 to the power of negative 3. So we've got 1 plus the power of negative 3 times the 5x over 2 plus the negative 3, I deduct 1 from the power, so negative 4 over 2 factorial times 5x over 2 to the power of 2. And then we've got minus 3 times minus 4 times minus 5 over 3 factorial times 5x over 2 raised to the power of 3 plus dot dot dot. I will proceed by expanding within the bracket, so we've got 1 over 8 times 1 minus 15x over 2 plus 75 over 2x squared minus 625 over 4x cubed plus dot dot dot, and I will expand further to arrive at 1 over 8 minus 15x over 16 plus 75 over 16 x squared minus 625 over 32 x cubed plus dot dot dot. In question 2, we're given the curve C with this equation, and we need to find dy dx in terms of x and y. This is a question requiring implicit differentiation, so we differentiate from left to right. We apply all rules of differentiation as usual. If we happen to be differentiating a term in y, we put the dy dx term as well. So the derivative of x cubed is obviously 3x squared. And now for the derivative of 2xy, I will be applying the product rule of differentiation. The derivative of 2x is 2, and I keep the y, so plus 2y. And then I keep the 2x, and the derivative of y is simply dy dx minus 1 minus 3y squared dy dx. And all of this is equal to 0. Remember, we're trying to make dy dx the subject here, so we've got 2x dy dx minus 3y squared dy dx on the left hand side, and this is equal to 1 minus 3x squared minus 2y. I will factor out the dy dx on the left hand side, so we've got dy dx times 2x minus 3y squared being equal to 1 minus 3x squared minus 2y, leading to dy dx being equal to 1 minus 3x squared minus 2y, and all of it divided by 2x minus 3y squared. In part B, we're asked to find an equation of the tangent at the point 3, negative 2, giving our answer in the form ax plus by plus c is 0, with a, b, c being integers to be found. So I will start by evaluating the expression we just obtained for dy dx at the point where x is 3 and y is negative 2. This is equal to 1 minus 3 times 3 squared minus 2 times negative 2, and all of it divided by 2 times 3 minus 3 times negative 2 squared, which gives an answer of 11 over 3. And then using y minus y1 is mx minus x1, we arrive at y minus the negative 2 is equal to 11 over 3 times x minus 3. So on the left hand side we've got y plus 2, and we've got this being equal to 11 over 3 times x minus 3. I will cross multiply to get 3y plus 6 is equal to 11x minus 33. And if I collect everything on the left hand side, we arrive at 3y minus 11x plus 39 is equal to 0. In 3a, we've got f of x here to be 1 over x times 3x minus 1 squared, decomposed into partial fractions as shown, and we need to determine the values of a, b, and c. So I will start by multiplying throughout by the LCM, which is the x times 3x minus 1 squared. This leads to 1 being equal to a times 3x minus 1 squared plus bx times 3x minus 1 plus cx. Now this here is an identity, which means it holds true for any value for x. So obviously, if we set x is 0, this will vanish and this will vanish, and I'll be able to recover the value of a. So let's do that. We put x is 0, and this leads to 1 is equal to a times 3 times 0 minus 1 squared, leading to a being equal to 1. Now another nice value for x will be the value of x that will make 3x minus 1 0. So this leads to x being 1 over 3. So if we set x to be 1 over 3, we arrive at 1 being equal to simply a third c, because these two terms will completely vanish. So this leads to c times a third, and therefore 3 is equal to c. Now I'm running out of nice values for x, but remember this holds true for any value of x. So I'm just going to put x is 1 and evaluate everything, leading to 1 being equal to a times 3 times 1 minus 1 squared plus b times 1 times 3 times 1 minus 1 plus c times 1. So this leads to 1 is equal to 4a plus 2b plus c. Now we know the value of a to be 1, so it's 4 times 1, and we know the value of c to be 3, so plus 3, leading to 1 is equal to 7 plus 2b, and therefore negative 6 is equal to 2b, which means that b is equal to negative 3. In part b, we are asked to hence find the integral of f of x and then proceed in evaluating the integral with the limits of 1 and 2, giving our answer in the form of a plus ln b, where a and b are constants to be determined. Well, let's start with the integral of f of x, which I can write as 1 over x minus 3 over 3x minus 1 plus 3 over 3x minus 1 squared, according to the answer we obtained in part a. So this is simply the integral of 1 over x minus 3 over 3x minus 1 plus 3 times the 3x minus 1 raised to the power of negative 2 with respect to x. And I can proceed because all of these three expressions are standard integrals. The integral of 1 over x is simply ln of the absolute value of x. Then we've got minus 3. We've got ln of the absolute value of 3x minus 1. And I need to divide by 3, which is the derivative of the 3x minus 1. And then we've got 3 times 3x minus 1 to the minus 1 over minus 1. So I increase the power by 1, I divide by the new power, and I also divide by the derivative of the bracket, which is 3, plus the constant of integration c. And I will simplify this to ln of the absolute value of x minus ln of the absolute value of 3x minus 1 minus 1 over 3x minus 1 plus c. I will then proceed in II, which requires me to evaluate the integral with limits of 1 and 2. So I will simply take the expression we just obtained. We've got the limits of 1 and 2. I will start by substituting the upper limit of 2. This leads to ln of 2 minus ln of 3 times 2 minus 1 minus 1 over 3 times 2 minus 1. That's the upper limit substituted, minus the lower limit, which is ln of 1 minus ln of 3 times 1 minus 1 minus 1 over 3 times 1 minus 1, which leads to ln of 2 minus ln of 5 minus 1 over 5. Now the ln of 1 here is simply 0, so it vanishes. So we've got ln of 2 here, and the two negatives give me a positive. So plus ln of 2, and then we've got minus the negative 1 over 2 here. So we've got plus a half. Remember, I need to get my answer in the form a plus ln b, with a and b being integers to be found. So I will combine the logarithms together. We know that the sum of logarithms leads to the logarithm of the product. And then when I've got subtraction, then I divide within the logarithm. So we're looking at ln of 2 times 2 over 5. And we also have got the minus a fifth plus a half, which gives an answer of 3 over 10. And I will simplify this, leading to ln of 4 over 5 plus 3 over 10. In question 4, we've got the sketch of the curve C described parametrically with the parameter t attaining values between 0 and pi. And we need to show that dy dx is k root 3 tan of 2t, where k is a constant to be found. I will start by finding expressions for dx dt and dy dt. So dx dt is root 3, and the derivative of sine 2t will simply be 2 cos of 2t, which gives me 2 root 3 cos of 2t. And for dy dt, we need to differentiate the 4 cos squared t, the expression for y. So it's 4, and we get the power down. We deduct 1 from the power times the derivative of the bracket. This leads to minus 4 times 2 sine t cos t, because the 2 sine t cos t is exactly the double angle formula for sine 2t. So we get minus 4 sine of 2t. And let's recall that dy dx is given by dy dt over dx by dt. So in our case, we're looking at minus 4 sine of 2t over 2 root 3 cos of 2t. Well, obviously we recognize sine over cos as giving me tan. We also have got simplification of the 4 with the 2, leaving me a 2 here. I will then multiply top and bottom by root 3 in order to get the root 3 in the numerator. I'm trying to rationalize the denominator. So we get minus 2 root 3 over 3. The 3 in the denominator is coming from root 3 times root 3 times tan of 2t. And if I compare with the answer I had to arrive at, I can see that the k is the negative 2 over 3. So I simply state here that k is equal to minus 2 over 3. In part B, we're asked to find an equation of the tangent to C at the point where t is pi over 3, and we need to give our answer in the form y is ax plus b, where a and b are constants. Well, let's start by recalling the expressions for x, y, and dy dx in terms of t. We have been told that the parameter t has a value of pi over 3, which means that x is equal to root 3 sine of 2 pi over 3, which gives an answer of 3 over 2. Y is 4 cos of pi over 3 squared, which gives an answer of 1. And for dy dx, I will substitute t is pi over 3 to get minus 2 over 3 root 3 tan of 2 pi over 3, which gives an answer of 2. And proceeding with y minus y1 is mx minus x1. We're looking at y minus 1 is equal to 2 times x minus 3 over 2. I will expand the right hand side to get y minus 1 is 2x minus 3, leading to y is 2x minus 2. In question 5, we are given a sketch of part of the curve with this equation: x is greater than or equal to 0. We are told that the curve meets the x-axis at the origin and at the point A, and we need to find in terms of ln2 the x-coordinate of the point A. Well, we know that since A is a cut on the x-axis, this means that y is equal to 0, which means we need to solve for x minus x e to the x over 2 being equal to 0. I will obviously factor out the x, leading to x brackets 4 minus e to the x over 2 is equal to 0. This leads to x is 0, which is the origin, or alternatively we have that 4 minus e to the x over 2 is 0, leading to 4 is e to the x over 2. Now we'll take a ln of both sides, leading to a ln of 4 is equal to x over 2. And if I cross multiply, I get 2 ln 4 is equal to x. Now I can write 4 as 2 squared, so 2 ln of 2 squared is equal to x, and the power of 2 here can come down through the power law of logarithms, leading to 4 ln 2 is equal to x, which is the x coordinate of the point A. In part B, we're asked to find the integral of x e to the half x dx. I'll be using integration by parts here, which says that the integral of u dash v is simply uv minus the integral of uv dash. So we're looking at the integral of x e to the x over 2 dx. I will set my u to be x and my v dash to be e to the x over 2. So u dash is equal to 1. And v will be the integral of e to the x over 2, which is e to the x over 2, and I need to divide by a half. So the integral of x e to the x over 2 dx will be x times 2e to the x over 2 minus the integral of 1 times the 2e to the x over 2. So simply 2e to the x over 2 dx, which gives me 2x e to the x over 2 minus 2 e to the x over 2 divided by a half plus c, which of course simplifies to 2x e to the x over 2 minus 4 e to the x over 2 plus c. In part C, we're asked to find by integration the exact value for the area of R, giving our answer in terms of ln 2. So if I briefly go back to the diagram given, we've got the limits being 0 and 4 ln 2. This is the x-coordinate of the point A we found in part A. So we need to integrate. So R is equal to the integral from 0 up to 4 ln 2 of 4x minus x e to the x over 2 dx. So we are looking at the integral of 4x, which is 4x squared over 2, minus the integral of x e to the x over 2, which we have found through integration by parts in part B. So this gave me 2x e to the x over 2 minus 4e to the x over 2. The limits are 0 and 4 ln 2. So I will proceed in simplifying first of all. So we're looking at 2x squared minus 2x e to the x over 2 plus 4e to the x over 2 from 0 up to 4 ln 2. Now before proceeding into substituting the upper and the lower limit, let's go back to part A, where we have observed that e to the x over 2 is equal to 4. So I'm just going to write this here as a reminder. E to the x over 2 is equal to 4. So when I'm substituting 4 ln 2 and I've got e to the x over 2, I'm simply going to be putting 4. So we are looking at 2 times the 4 ln 2 raised to the power of 2 minus 2 times 4 ln 2 times e to the x over 2, which is simply 4 as we explained, plus 4 times 4. And if I substitute the lower limit of 0, this is 0, this is 0, this is going to be 4 e to the 0. So from the lower limit, we just have a 4. So we're looking at 2 times the 4 squared, so 2 times 16 times ln of 2 squared minus 2 times 4, which is minus 32 ln 2 plus 16 minus 4, leading to 32 ln of 2 squared minus 32 ln 2 plus 12. In question 6, we are asked to prove by contradiction that if a and b are positive real numbers, then a plus b is greater than or equal to 2 root of ab. So this is the proposition here. Well, in proof by contradiction, we always start by assuming the opposite. So we say suppose not, i.e. there exist positive reals a and b such that a plus b is strictly less than 2 times the root of ab. I will proceed by squaring both sides. So we've got a plus b squared being less than 4 times ab. So we're looking at a squared plus 2ab plus b squared being less than 4ab, leading to a squared minus 2ab plus b squared is less than 0, which I should recognize as a perfect square. So we're looking at a minus b all squared being less than 0, which I should be able to recognize as a contradiction, because if I square any real number, then it's surely a non-negative result. So I say contradiction, since a minus b all squared should certainly be greater than or equal to 0 for any real number a and b, and therefore this leads to the conclusion that a plus b is greater than or equal to 2 root of ab for all real positive numbers. In question 7, we are given a sketch of the curve C with these parametric equations. T is between 0 and 2 pi inclusive. We need to show that x plus y is 2 root 3 cos t. I will start by reminding ourselves of the compound formula for cos of a plus b, which says that this is cos a cos b minus sin a sin b. So if we consider x plus y, then we're looking at 4 cos of t plus pi over 6 plus 2 sine t. So we're looking at 4 cos t cos of pi over 6 minus 4 sine t sine of pi over 6 plus 2 sine t. Now cos of pi over 6 is root 3 over 2. So we've got 4 cos t root 3 over 2, and then minus 4 sine t, and sine of pi over 6 is a half. So I put the half plus 2 sine t. Now all of this simplifies to 2 root 3 cos t minus 2 sine t plus 2 sine t. Obviously, the sine t terms will cancel out, and therefore this leads to 2 root 3 cos t as required. In part B, we need to show that the Cartesian equation of C is x plus y all squared plus ay squared is b, where a and b are integers to be found. Well, let's start by recalling that we have established that x plus y is 2 root 3 cos t, and we also know that y is 2 sine t. This means that x plus y over 2 root 3 is equal to cos t, and also y over 2 is equal to sine t. We also know that cos squared t plus sine squared t is equal to 1 for all t. So I will be replacing cos t with x plus y over 2 root 3, leading to x plus y over 2 root 3 all squared, plus the sine t, which is y over 2 all squared, being equal to 1. So we've got x plus y raised to the power of 2 over 12 plus y squared over 4 is equal to 1. I will multiply throughout by 12, leading to x plus y squared plus 3y squared is equal to 12. In question 8, we've got water being heated in a kettle. At time t seconds, the temperature of the water is theta degrees Celsius. We are given this differential equation describing the rate of increase of the temperature of the water. We are additionally told that when t is 0, theta is 20, and we need to solve this differential equation to arrive at theta is 120 minus 100 e to the minus lambda t. Well, we know that with this differential equation, I will proceed by separating the variables, which means I will collect the theta terms with the theta on the left-hand side and the t terms with the t on the right-hand side. So we are looking at 1 over 120 minus theta d theta being equal to lambda dt. I will integrate both sides. So on the left-hand side, it will give me ln. So we've got ln of the absolute value of 120 minus theta, and I need to divide by -1, which is the derivative of 120 minus theta. On the right-hand side, we've got lambda. Lambda is a constant, it's a number, so its integral with respect to t will simply be lambda t plus c. And I can then proceed with the fact that when t is 0, theta is 20. This leads to minus ln of 120 minus 20 is equal to 0 plus c, and therefore minus ln of 100 is equal to c. So my differential equation is negative ln over 120 minus theta is equal to lambda t minus ln over 100. I will start by multiplying everything by negative 1, leading to ln over 120 minus theta is equal to minus lambda t plus ln over 100. I will now collect the logarithmic terms on the left-hand side, leading to ln over 120 minus theta minus ln over 100 being equal to minus lambda t. I will write everything as a single logarithm on the left-hand side, so we're looking at ln over 120 minus theta over 100, and this is equal to minus lambda t. So I will remove the ln by doing e to the minus lambda t. So we've got 120 minus theta over 100 is equal to e to the minus lambda t. If we cross multiply, we get 120 minus theta is 100 e to the minus lambda t, leading to 120 minus 100 e to the minus lambda t is equal to theta as required. Now when the temperature of the water reaches 100 degrees Celsius, we switch it off. Given that lambda is 0.01, find the time to the nearest second when the kettle switches off. So this is the equation we've got for theta. I will be replacing lambda with the value of 0.01 and theta with the value of 100. This leads to 100 being equal to 120 minus 100 e to the minus 0.01 t. So we are looking at 100 e to the minus 0.01 t being equal to 20. I will divide both sides by 100, leading to e to the minus 0.01 t being equal to 1 over 5. I will get rid of the exponential term by taking ln of the right hand side. So we've got negative 0.01 t being ln of 1 over 5, and therefore t is 1 over the negative 0.01 times ln of 1 over 5. This gives an answer for t of 160.943 ... and therefore we conclude that to the nearest second we are looking at a time of 161 seconds. In question 9, we're given the equation for the line L1. Mu is a scalar parameter. We are told that the point A is a point on the line where mu is 1, and we need to find the coordinates of A. So I will simply be substituting mu is 1. This leads to A having coordinates of 8 plus 1 times the negative 5, 1 plus 1 times the 4, negative 3 plus 1 times 3, which leads to the coordinates of the point A being 3, 5, 0. We're then given the point P with position vector 1, 5, 2, and we are told that the line L2 passes through the point P and is parallel to the line L1, and we need to write down a vector equation for the line L2. Well, we know that since the two lines are parallel, they have the same direction vector, and the direction vector is the negative 5, 4, 3. I will use the 1, 5, 2 here as the position vector, and therefore the line L2 has equation R is 1, 5, 2 plus a scalar lambda times negative 5, 4, 3. In part C, we're asked to find the exact value of the distance AP, giving our answer in the form k root 2. I will start by finding the vector AP. So I'll be doing the vector P minus the vector A. The vector P is 1, 5, 2, and the vector A, we found this in part A to be 3, 5, 0. This leads to negative 2, 0, 2. And to find the magnitude of AP, I simply take each entry, the I, the J, and the K component, I square them and I add them up and I take the square root. So that's going to be negative 2 squared plus 0 squared plus 2 squared, all square rooted, which gives an answer of 2 root 2. We're then asked to find the value of cos theta, where theta is the acute angle between AP and L2. So I will be doing the dot product between the vector AP and the direction of the line L2. The vector AP was negative 2, 0, 2. The vector corresponding to the direction of the line L2 is the negative 5, 4, 3. So the dot product of these two should be equal to the magnitude of the minus 202. So minus 2 squared plus 0 squared plus 2 squared square rooted times the magnitude of the negative 543. So minus 5 squared plus 4 squared plus 3 squared square rooted times the cosine of theta. Now when I'm applying the dot product, I multiply the I with the I, the j with the j, and the k with the k, and I add them up. This leads to 10 plus 0 plus 6 being equal to 2 root 2 times 5 root 2 times the cosine of theta. So we've got 16 being equal to 20 cos theta. Remember, we're not trying to find theta, we're trying to find cos theta. So if I divide both sides by 20 here, we arrive at cos theta being equal to 4 over 5. Now we are told that there's a point E lying on the line L2. We are told that AP is equal to PE, and we need to find the area of the triangle APE. Well, I will start by drawing the two lines, which we know they are parallel. We've got the point P on L2, we've got the point A on L1, we've got a point E somewhere on L2, and we know that the angle theta is the angle between L2 and AP. We also know that we need to find the area of this triangle, and we are given that the distance PE and the distance AP are equal, and the distance is 2 root 2. So we're trying to find the area of this isosceles triangle here. We also know that cos theta is 4 over 5, so it makes sense to draw a right angle triangle here. We've got cos theta being 4 over 5, so that's adjacent over hypotenuse, and this means that the opposite is 3. So we're looking at sine theta being equal to 3 over 5, and therefore the area of the triangle APE would be a half times AB sine C. So it's a half times 2 root 2 times 2 root 2 times the sine of theta, which is 3 over 5, which gives an answer of 12 over 5 units squared for the area of the triangle. In part F, we need to find the coordinates of the two possible positions of E. Well, let's start by recalling the equation for the line L2. It's 1, 5, 2 plus lambda times negative 5, 4, 3. This is the diagram we drew before. We know that the point P here has coordinates 1, 5, 2, and the point E being a point on the line L2. This means that we can express its coordinates in terms of lambda. So we're looking at 1 minus 5 lambda, comma 5 plus 4 lambda, comma 2 plus 3 lambda. The whole idea is to find the possible values for lambda and proceed to find the possible coordinates for the point E. And this will be based on the fact that we have the magnitude of PE. So I will start by finding an expression for the vector PE, which is simply going to be given by the vector E, which is 1 minus 5 lambda, 5 plus 4 lambda, 2 plus 3 lambda, minus the vector P, which is 1, 5, 2. This gives an answer of negative 5 lambda, 4 lambda, 3 lambda. And I will now find an expression for the magnitude of PE in terms of lambda, which is going to be minus 5 lambda squared plus 4 lambda squared plus 3 lambda squared and all square rooted, which gives me 25 lambda squared plus 16 lambda squared plus 9 lambda squared under a square root. And this simplifies to the square root of 50 lambda squared, and we know that this is equal to 2 root 2. So I can remove the square root by squaring both sides, leading to 50 lambda squared is equal to 8, and therefore lambda squared is 4 over 25, which means that lambda is equal to plus minus 2 over 5. Now I will substitute lambda is equal to 2 over 5 to find the first possible position for E. So we're looking at 1 minus 5 times 2 over 5, comma 5 plus 4 times 2 over 5, comma 2 plus 3 times 2 over 5. This simplifies for the coordinates of E to be -1, 33 over 5, and 16 over 5. I will proceed with the lambda being -2 over 5, which means that E has coordinates 1 minus 5 times the -2 over 5, 5 plus 4 times the -2 over 5, 2 plus 3 times the -2 over 5, and therefore we conclude that the second possible position for E has coordinates 3, 17 over 5, or 4 over 5.